we are with Unit 8, Lesson 1, the area of squares and their side lengths. Today we're going to start by looking at two different figures, two different regions, and decide which area, which shaded region is larger, and explain the reasoning. One way that we can look at this is either through translation, rotation, or a combination of those transformations to think about how could I move these different shaded regions together to fit in like puzzle pieces. Perhaps you wanted to take this region right here and translate it down here, and then this one up to here, and we can see pretty clearly that it fills up half those regions. A good mathematical way to think about this is to look at the total area. We have 2 units by 4 units, so a total of 8 square units. And then we can look at what we have shaded. If we look at just 1/4 of this, we see a 2 by 1 array. So we see this 1/4 of this is an area of 2 square units. Within these 2 square units, we see half of that value is shaded. So we have 1 square unit is shaded. What we're doing here is looking at the area of a triangle, which is equal to 1/2 the length times the width, or perhaps you're more familiar with length times width divided by 2. Either one is totally fine. Understanding that logic tells me that if this area that's shaded is 1 square unit, then the unshaded area is 1 square unit as well. And so through that logical process, we can understand that this would be 1, 2, 3, 4 shaded regions, or 4 square units that are shaded. We can use the same logic here on the right by looking at these pieces and just taking one part of it and seeing 2 by 1 and recognizing that that's 2 total square units, and we cut that in half using the triangle to have 1 square unit that's shaded. We see this triangle here is 1 unit, this one is 1, this one is 1, this one is 1, and the one in the middle is 1. So we see 5 square units that are shaded. Through that reasoning, we can see that figure B is the larger shaded region. Another way we could have thought of that is taking the white areas and recognize there are 4 white areas and taking 9 square units minus 4 square units to still get us 5 square units. What we're doing here is what we call decomposing the areas. Decomposing the area means to take apart the regions that are around it, or take apart pieces of the figure to be able to figure out what the areas are and the dimensions are to be able to actually calculate the area of another region. One way that I kind of think about that is I think about the area of the whole minus the area of the whole, meaning the piece in the middle. So when I look at this one right here, I can see that there could be a larger square that's being given right here. I see that that square has a total square value of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A total area covered by just the little areas right next to the shaded regions. This is 100 square units total. If I look at the unshaded regions, I can recognize that those pieces are all the same size. I can see that they have a size of 1 by 9 on the triangle, or half of 9 square units. So each of these are 4.5 square units. If I were to take this piece right here and match it with this piece right here, I would see a total of 9 square units. You can kind of see that if this triangle right here is the exact same size as this triangle right here. So what I can think of is I can take that 100 square units and I can subtract 4 times 4.5, which is going to be 18. So 100 minus 18 will give me 78 square units. Okay, looking at figure B, I can think about the exact same thing, and I can work with these pieces right here and think about the area of the whole thing minus the area of the hole in the middle. But it would be something where I would work this out with recognizing these triangles on the side. This triangle on the side has one side length that is 1, 2, 3, 4, 5 units. And this one over here is 1, 2, 3, 4, 5 units. And I can go and just double check and confirm that there's 5 units on each of these all the way around. And I can see that there's, if I take each of them together, That would make a total area of 25 square units for these two, 25 square units for these two. Again, we have 100 square units for the total area. And if we subtract the values of 5 times 5, or half of 5 times 5 is 12 and a half. I have 4 of those regions that are 12 and a half. I know that 2 of them together are 25, so this is 100 for the total, minus 50 and minus 50 to give us a total of 50 square units. Figure C is a little bit different. Figure C gives us the dimensions off on the sides, so this is pretty helpful. I can see that I have 4 triangles that are all of the same area, and those 4 triangles of the same area are 7 by 3, or 21. But then we talk about dividing it in half, because the triangle, that's 21 divided by 2, so 10 and a half. What we know about the total side length is we have a 10 by 10 because we see 7 plus 3. So a 10 by 10 array is 100 square units. Again, minus 4 regions that are white, that are unshaded, at half of 21, or 21 halves. 21 halves, as we know, is 10 and 1 half, so perhaps that might be a little bit easier for us to work with. 4 times 10 and 5 tenths, which we can also subtract out as 42, giving us a total area of 58 square units. All right, if you're ready for more, go ahead and give this one a try that has multiple different areas, multiple regions. Any triangle in the with a base of 13 and a height of 5 has an area of 65 halves. So go ahead and take a look at these pieces and give this one a shot. 1.3, estimating side lengths from areas. We can work on that same type of piece just by estimating side lengths by looking at the length of it. If we have a horizontal length or a vertical length on a grid, it's pretty easy. But when we get to ones that have a length that is diagonal, it makes it a little bit harder. So first thing, for part A, what we want to look at is we can just simply count the region there, or count the spaces that are given across the horizontal, and recognize that we have 1, 2, 3, 4, 5. So we have 5. 1, 2, 3, 4, 5. 5 by 5. I'm going to skip B for the moment. And C, we have 1, 2, 3, 4, 5, 6. And going down, 1, 2, 3, 4, 5, 6. We have 6 going that way. So we go, the side lengths of square A are 5. The area would be 5 times 5, which is equal to 25 square units. For C, we saw 6 units for the lengths. And what's the area? That could be the same thing as 6 squared, which is 36 square units. And it says, what's the area of square B? What is its side length? Use tracing paper to check your answer to this. I'll go ahead and use that tracing paper, but think about a way that we could actually make this work. What we could do to recognize these values is we can work on this value where we talked about just a moment ago, of decomposing that triangle and seeing how that area works. We could find the total area by taking the value of, again, one of these rectangles that includes that triangle. And we can see the area of one of those triangles right here. We can see that area of a triangle here and here and here. And we see 4 equal triangles plus 1 unit right in the middle. We can take the values here. This is a 3 by 4. So 3 by 4 would give us 12 square units right here. 4 times, so that's 36. But we have to remember that we're working with triangles, so we have to cut it in half. We can understand then that this triangle in the middle is half of 12, so it's 6 square units here, 6 here, 6 here, and 6 here. So 6 times 4 is 24, plus the one in the middle is 25. And understanding that we have a total area of 25 square units, we can work backwards and take the square root of that to give us 5 units for each side length. Okay. So now find the areas of squares D, E, and F. Which of these squares must have a side length that is greater than 5 but less than 6, and explain how you know. Again, working with the same type of strategy that we just did a moment ago, we can go ahead and take a look at the figures and recognize figure D has an area of 2 by 4. So let's go ahead and kind of shade these out and get some triangles here. I see 4 equal sized triangles. There are a 2 by 4 triangle with 4 units on the inside. 2 by 4 is 8, half of that is 4. So we see that this is regions of 4 all the way through. So this is 4 times 5 for a total area of 20. So D equals 20 units squared. You can see E, if we work the same type of thing. We see 9 units on the inside. On this one, we see 1, 2, 3, 4, 5, 6, or 5 by 2, which is 10. Half of that will be 5. So we have 5s all the way around here. 5 times 4 is 20. So E has 29 square units. And then F, we have 3 by 5, which is 15. And then half of that will be 7.5. We'll double check that again. 1, 2, 3, 4, 5. 1, 2, 3. So half of that, we have 7 5/10. And then the middle is 4. So we have 7 5/10, 7 5/10. There's 15. Plus 15 is 30, and 34 square units. Now the question says, which one must have a side length that is greater than 5 but less than 6? Explain how you know. Well, 20 is not a perfect square, neither is 29, neither is 34. But taking the square root, we can make estimates of this. I know that 20 is between 16 and 25, and the square roots of 16 and 25 are 4 and 5. So this one, the square root of 20, will be somewhere in between 4 and 5. 29 is between 25 and 36, which is square roots of those ones are 5 and 6. So we know the square root of 29 must be between 5 and 6. And then 34 is between 25 and 36 as well. So we know the square root of 34 must be somewhere in the middle of that. But we know that that value must also be greater than this one here. This one is probably closer to 5 point something, but this one is probably closer to, or 5.2, 5.4. It's less than 5.5. This one's more than 5.5. So which of these squares must have a side length that's greater than 5 but less than 6? We recognize that figures E and F will have that value because we know that their approximate square roots are greater than what we see right here. On 1.4, we actually see something that's a digital version where you would be getting paper from me, but that's not going to happen today for the same reason we've never done that. Take a look at the lesson summary. The area of the square with side lengths 12 is 12 squared, or 144 square units. Side length of a square with 900 units is 30 units because of 30 squared is equal to 900. Remember that we can always work backwards if we're given the end result as 144 square units. We can take the square root of that to find the side length would be 12 square units, and likewise 900, the square root of that would be equal to 30 units per side length. Sometimes we want to find the area of the square, but we don't know how to, or don't know the side lengths. For example, we can find it right here. We would talk about that same piece down here in the bottom of using the square roots to be able to find those values. So take a look through it, read it carefully. Please reach out for any questions. Make sure you have a great day. Take care now.